This video is about gases, and specifically it's about Gay-Lussac's law. Gay-Lussac was a French scientist of the early 1800s, and he was the first one to, or he gets the credit for, explaining the relationship between the pressure of a gas and its temperature. In this video we're going to make a connection between things we can measure, pressure and temperature of a gas, and how we can express symbolically what the relationship is. So we can write an equation, we can do some calculations based on our observations of pressure and temperature. So here's a can of shaving cream. You've seen a can of shaving cream before, and we'll shake it up because we want the ingredients inside to be mixed. And you know that when we press the button on the can, some shaving cream will come out. There we go. Why does that happen? Well, inside this can, in addition to the soap and the lubricant that we're interested in, are some gases. And those gases are in the can under pressure. And so when we press the button down and open up the valve at the top of the can, those gases want to escape to the room where the pressure is lower. So the gases are anxious to force their way out. And if they're mixed just right with the soap and the lubricant, they'll bring some of that along. And so we can get the product we want out of the can by capitalizing on the difference in pressure between the inside of the can and the outside of the can. This can has a warning label on it. It says, "Do not puncture or incinerate. Do not heat for warm lather or any other purpose. Do not keep where the temperature will exceed 110 degrees Fahrenheit." So why is that? Well, suppose we did heat this can up. What would happen to the gas particles that were inside? Temperature is a measure of how fast the particles are moving. So when we add heat and raise the temperature of the gas, it's because the particles are moving faster. When the particles are moving faster, they can get from one side of the container to the other side of the container more quickly. And therefore, they bang into the walls of the inside of the can more often. Those collisions with the walls are what causes pressure. So, if we increase the temperature of the can, the particles move faster, they collide with the walls more often, and they increase the pressure inside the can. If the pressure increases too much, the can might not be able to stand the pressure and it might break apart. And that might happen violently, and we might get little pieces of metal flying around, and it might be a very dangerous situation, which is why there's a warning label on the can. But the particles, when they're heated, move faster, they collide more often, so as temperature goes up, pressure goes up. That is Gay-Lussac's law. As the temperature of a gas sample increases, the pressure of that sample also increases. We can say Gay-Lussac's law another way also. As the temperature of a gas sample decreases, the pressure of that sample decreases too. So, in other words, temperature and pressure of a gas move in the same direction. To put it a little bit more mathematically, pressure and temperature are directly related. When one increases, the other increases. When one decreases, the other decreases. These together are Gay-Lussac's law. So we can do this symbolically. We can say that as the temperature increases, pressure increases, and we can write it in this way. As the temperature decreases, pressure decreases. So this might be a way to help us remember the relationship between temperature and pressure. Here's a mathematical expression of Gay-Lussac's law. So we can get down to specifics. We can specifically say how pressure and temperature are related. So pressure 1 divided by temperature 1 equals pressure 2 divided by temperature 2. So the ratio of pressure to temperature in a gas sample stays the same. Here are our subscripts. Pressure 1 is the pressure that's measured early in the experiment. It's the first pressure. And temperature 1 is the temperature that's taken at the same time pressure 1 is measured. Pressure 2 and temperature 2 come later on in our experiment. They're what happens after a change has occurred. Gay-Lussac's law is usually written as proportions. It's usually written in this way. But we can rearrange this equation using the rules of algebra to get this equation down here. It's exactly the same thing written in a different way. And some people think this is an easier equation to start with when we're doing calculations. Note the subscripts. P1 times T2 equals P2 times T1. Both of these equations say the same thing. Both of them say that as pressure increases, temperature increases, or as pressure decreases, temperature decreases. Pressure and temperature are directly related. Now, what about units of measure? So for pressure, we can use any units of pressure so long as pressure 1 and pressure 2 are in the same unit of measure. What about temperature? Well, temperature must be expressed in Kelvin. Usually in science we measure temperature in degrees Celsius. If we want to convert to Kelvin, we add 273 to the temperature in degrees Celsius to get Kelvin. Temperature must be in Kelvin whenever we're calculating with Gay-Lussac's law. Let's try an example. Let's think about a tightly closed, rigid glass bottle. Tightly closed, no air can get in or out. A glass bottle, it's rigid. The volume of the bottle won't change, so the volume of the gas inside the bottle won't change. So that bottle is filled with air to a pressure of 1.5 atmospheres at 22 degrees Celsius. And we want to find out what the new pressure of the bottle is when the temperature is lowered to 5 degrees Celsius. A perfect problem for Gay-Lussac's law. Number of gas particles is constant, temperature is constant, pressure is increasing, or pressure is changing, that is, but we don't know how yet, as temperature is decreasing. So if we look at the rules of the problem, or the words of the problem, we can see that our first temperature is 22 degrees Celsius, that's T1. We need to express it in Kelvin, so we added 273 to get the temperature in Kelvin. The original pressure, 1.5 atmospheres. Things change. The temperature goes down to 5 degrees Celsius, or 278 K, and we want to find out what the new pressure is when we make that change. So let's take Gay-Lussac's law. There's the equation. Let's substitute our values. Pressure 1, 1.5 atmospheres. Temperature 2 now, 278 K. Pressure 2 is our unknown. Temperature 1, 295 Kelvin. So once we've made those substitutions, now we've got a math problem. We want to isolate our variable, and let's get rid of this. We'll isolate our variable by doing this step here, where we take both sides of the equation and divide by 295 Kelvin. That leads us to the expression below. Pressure 2 equals 1.5 atmospheres times 278 divided by 295, which is 1.41 atmospheres. So from the beginning of the problem to the end, pressure went down. Remember, our original temperature was 22 degrees Celsius, or 295 Kelvin. Temperature went down. So when temperature went down, pressure went down. That's what we expect from Gay-Lussac's law. Pressure and temperature are related directly, and that's what happened in this problem. There you have it. There's an example of Gay-Lussac's law.